Okay, everyone, I promise this is the last part. I actually want to go back. I forgot to mention where I'm getting these KB values from. So you know the one where you had to determine the KA and the pKa? These KB values were given in other problems in the same section. So for example, this N2H4 was given in the practice problem on page 321. And this one here for the CH3NH2 was given in the sample problem on page 320, just so you know. You're like, oh, where the heck did she get those from? Because you don't have this in your chart, actually. Just so I can kind of clarify that. Okay, so let's take a look at the last section here. So this is where you would have, you're calculating KB, but you're given the initial and the pH or pOH of a solution. Okay, so let's take a look here. So we have a 0.4 mole per liter solution of a weak base, and we're told the pH value. Calculate the KB of methylamine and the percent ionization. Compare your calculation of this KB value with the sample problem involving methylamine. Okay, so we'll get back to the sample problem part first. Let's calculate the KB and the percent ionization first. Okay, so we have CH3NH2 plus water. So that's going to give us our hydroxide and CH3NH3 plus, right? So because they give us the pH, right, by determining, so the pOH is 14 minus the pH, right? So we get a pOH, pardon me, of 11, which means, oh, no, I lied, 1.1. And then we're going to have a hydroxide concentration equal to 0.0794 moles per liter. So here our ice table, right, we have 0.4, and then this is 0 minus x, 0.4 minus x, plus x, plus x, x, x. Okay, so KB is equal to x squared, but we know what x is, right? So we can actually just plug this in. 0.0794 moles per liter squared over 0.4 minus that. So our KB value here ends up being 0.0197. And to 2 sig figs, so 0.020. Okay, so then we have to determine the percent ionization, right? So in other words, we're looking at the product versus the initial amount. So in this case, our product amount is 0.0794, right, our hydroxide, over the initial amount is 0.4. So it ends up being approximately, I believe it's 20%. Let me just recalculate that for a second. Okay, 0.0734. Yeah, 19.9. And percentage usually, to be honest, percentage is not looked at for sig figs, but if we had to, we put 20 with a dot for our 2 sig figs. So that's our percent ionization. So let's look at the second part. It says compare your calculation of this KB, which is here, to the KB in the other sample problem. So the KB in the sample problem, let's take a look. The sample problem for CH3NH2 is given as 4.4 times 10 to the negative 4. Okay, so this KB, so this one is KB volume temperature. What my indicator? So I'm under the assumption that this KB is at 25 degrees Celsius from the sample problem, because we used the Ka value. No, we didn't. Sample problem doesn't indicate temperature, so I'm going to assume that that's what this is, because this is saying what might this indicate about the temperature of this solution. So this solution has a higher Kb. So I would assume that the solution that we're dealing with in this problem would have a higher temperature because it's pushing towards a higher value of product. Now, can we say that concretely? We don't really know if this is endothermic or exothermic. However, in general, when you're dealing with ionization, right, the faster these original reactants are together in water, right, the higher the temperature is, you are giving it more energy with its collisions. So the chances are that you're going to have a higher temperature with a higher Kb because you're pushing towards creating more product. Kb. So I would assume really we can't really say too much, except I think the temperature is higher than 25 degrees. In general, I think that's pretty much the only thing we can concretely say. How much? We don't know. We won't have a way of measuring that with the information given. Okay, so then we have number 2. One of the most effective substances for pain relief is morphine, developed in the 1810. Okay, so we have a concentration of 0.01 mole per liter. We have a POH. Calculate the Kb and pKb for morphine. Morphine is a weak base. Okay, so it says let's use these symbols. Probably the formula for morphine is incredibly large. So we have H more plus hydroxide, right? So we have the initial, and then they're telling us the POH. So remember, it's 0, 0. This ends up being X minus X, 0.01 minus X. But then telling us the POH, right, we can figure out the concentration of hydroxide by doing 10 to the negative 3.90, which will end up being 1.26 times 10 to the negative 4, which we can then plug in for our Kb. 1.26 times 10 to the negative 4. And this is going to, squared, and this is going to be 0.01 minus that. So we end up with a Kb value of, 1.61 because we're going to continue with this. But I would say then 1.6 times 10 to the negative 6. But then for the pKb, to do the negative log, right, let's do that. This should end up being to 2 decimals, 5.79. Okay, quinine, which is another very large molecule, is used for the treatment of malaria. So calculate the Kb, we have the initial concentration, we have the pH. So really we would need the POH, right, which is 4.16, 14 minus that. The concentration of hydroxide is 10 to the negative of that, which will end up being 6.198 times 10 to the negative 5. So really Kb, I mean, we're used to the pattern by now. This is going to be our X squared, and then we have our initial minus that. Kind of nice when they give us the X value or a way to figure it out. And then we get a Kb value here of 2 sig figs. So 3.3 for your final answer times 10 to the negative 6. Oh, mamma mia. We are done. Okay, so my apologies, but basically those are kind of all the different types of scenarios you're going to see for these calculations. It's very important, especially even leading into the next chapter, that you know the relationship between Ka, Kb, pKa, pKb, hydroxide, hydronium, Kw, and all of the different interactions and ways that we can determine those. Okay, so if you have any questions, I will address them tomorrow in class. If not, have fun tackling these review questions. You're going to be fine. Have a good day.